Welcome to this explainer. Today we're diving into something genuinely mind-bending, Grover's algorithm. Imagine for a second that you're tasked with finding a single needle in an infinite, completely unstructured haystack. In the classical computing world, this is an absolute nightmare scenario. But in the quantum realm, there's actually a way to manipulate the very fabric of probability to make that needle practically jump right out at you. We're going to explore the magic of amplification today, breaking down the exact mechanics of how quantum computers achieve what seems totally impossible. Okay, let's dive into this. Here is our roadmap for today. We'll start with the unsorted database problem, move on to the quantum secret of wave interference, look at the phase flip, break down the diffusion operator, see how we rotate toward the answer, and wrap up with the quadratic speedup. Section 1. The unsorted database problem. Finding the needle. So picture this. I hand you a massive physical phone book with a million names. But here's the catch. They are entirely out of order, random. And I ask you to find the name attached to one specific phone number. What do you even do? How on earth do you find one specific item in a massive unsorted database without literally checking every single one? Well, classically, you don't really have a choice, right? You just have to check them one by one. On average, you're going to have to slog through half that database before you hit the jackpot. Worst case, you check all n items. We call this an order of n, or O of n, operation. But Grover's algorithm, it throws that out the window. By checking the data in a state of quantum superposition, it spots the answer in roughly the square root of n steps. That is a colossal, game-changing difference. And to see how it pulls this off, we've got to look at the physics. Section 2. Quantum secret, wave interference. This right here is the underlying secret weapon of pretty much all quantum computing. See, quantum states aren't just dry probabilities, they actually act like waves. And waves have amplitudes that can be positive or they can be negative. Wave interference is this wild phenomenon where amplitudes with the same sign add up to create a bigger wave. That's constructive interference, boosting the probability. But when they have opposite signs, they cancel each other out entirely. That's destructive interference. So Grover's algorithm is essentially this highly tuned precision machine. It's built to intentionally cause constructive interference for the right answer and destructive interference for all the wrong ones. Now, what's really interesting about this slide is how we can visualize this with a super simple classroom analogy. Imagine a class with 5 students, A, B, C, D, and E. Let's say they all start out with an equal score of 5 marks. In our quantum system, this perfectly represents our initial uniform superposition. Every possible answer has an equal positive amplitude. So the class average right now, it's exactly 5. Okay, so now we introduce what's called an oracle. Let's say we're looking for student C. The oracle knows exactly who student C is, but it's not just going to hand us the answer. Instead, it marks student C by flipping their phase. Student C's score goes from a positive 5 to a negative 5. Now, to the naked eye, if you were to measure this, the probabilities actually haven't changed at all. Why? Because probability is just the square of the amplitude, and negative 5 squared is exactly the same as positive 5 squared. But look closely at what happens to the class average. We've got 4 students with 5 and 1 with negative 5. Total is 15. Divide that by our 5 students, and bam, our new class average plummets from 5 down to 3. Here is where the absolute genius of amplitude amplification really kicks in. The algorithm performs a mathematical trick called inversion about the mean. The formula is pretty straightforward. The new amplitude equals 2 times the average minus the old value. Mathematically, you'll see this written as 2a prime minus a. Let's run the numbers for our target student C. The new average is 3. 2 times 3 is 6. The old value was negative 5. So 6 minus negative 5? That equals 11. Student C's amplitude just shot way up from 5 to 11. And what about everyone else? 2 times 3 is 6, minus their old value of 5 equals 1. So the wrong answers literally shrank from 5 down to 1. We've successfully amplified our target and totally suppressed the noise. How cool is that? Section 3. Phase flip. Marking the target. So the crucial point is how we map this analogy back onto an actual quantum circuit. One complete Grover iteration is made up of 2 very precise steps. Step 1, the oracle applies a phase flip. It targets the specific state we want and flips its amplitude to negative. But, like we just talked about, you cannot measure that phase flip directly. It's invisible. So step 2 is the diffusion inversion. This takes that invisible phase change and forces it out into the open, converting it into a massive probability spike by inverting all the amplitudes around that new lower average. Section 4, the diffusion operator explained. All right, let's lift the hood and look at the mathematical engine driving that second step. The diffusion operator, which we call D, has a very specific formula. D equals negative h and n I naught hn. What exactly does that mean for us? Well, the hn stands for Hadamard gates. These are what we use to throw our qubits into superposition and also pull them out. The I naught part is an operation that specifically inverts the amplitude of the zero state. But hold on. Our goal is actually to invert the amplitudes of all the other states, right? Not the zero state? So to correct that little algebraic quirk, we just multiply the whole shebang by a negative sign. This really elegant sequence of operations mathematically executes the exact inversion about the mean that we just saw in our classroom analogy. Section 5, rotating toward the answer. And this brilliantly illustrates that beyond all the algebra, there's actually this beautiful geometric reality to what the algorithm is doing. There's a saying in math, 2 reflections equal a rotation. If you picture a 2D plane, the oracle essentially reflects our quantum state vector right across an axis. Then, the diffusion operator reflects it a second time. Geometrically speaking, when you reflect a vector twice, you rotate it. So with every single Grover iteration, we are literally rotating our quantum state vector closer and closer, aiming it directly toward the axis of our correct answer. But wait, here's a critical subtlety that often trips people up. You absolutely cannot just let this loop run endlessly. Because it is a literal geometric rotation, if you run too many iterations, your state vector is going to swing right past the target axis. The probability of finding your target will peak, and if you just keep calculating, it's actually going to drop back down because you've overshot the answer. Precision really matters here. You have to stop the algorithm at exactly the optimal number of iterations, which, again, is roughly the square root of n. Section 6, the quadratic speedup. So why does all this quantum rotation and wave interference actually matter? Why does it change the computing world? Just look at the massive disparity on this chart. If you've got a database of 1 million items, your standard classical computer needs roughly 500,000 steps on average to find a specific entry. Grover's algorithm, leveraging that order of square root and n scaling, it takes about 1,000 steps. Let that sink in. 500,000 versus 1,000. And it scales insanely well. If your database grows to, say, 1 trillion items, the classical computer takes 500 billion steps. The quantum computer, just 1 million. It literally turns an impossible, lifetime-long task into a quick calculation. The real-world implications of this are frankly staggering. The most immediate impact we're seeing is on cryptography. Think about AES-128 encryption. It protects vast amounts of the world's secure data. It relies on the assumption that a classical computer would need 2 to the power of 127 operations to brute force the key. Grover's algorithm slashes that down to 2 to the power of 64 operations. That fundamentally breaks the current security standard. It's exactly why major industries are already scrambling to transition to 256-bit encryption. Beyond that, it totally revolutionizes things like SAT solving, executing massive database searches, and finding hash collisions in cybersecurity. Grover's algorithm proves that quantum computers don't run on magic, right? They just systematically amplify what's right and suppress what's wrong through interference. It's pure, brilliant physics. So I'll leave you with this thought to chew on. If an algorithm can turn a 500 billion step classical problem into just 1 million quantum steps, is our current digital security already a relic of the past? Thank you so much for joining me for this explainer. Keep asking questions, and I'll see you next time.